According to the reaction carbon dioxide and hydrogen giving methanol and water, it can be observed that the proportion of hydrogen is 3 times the proportion of carbon dioxide. In order to start with the mass balance, we had to calculate the molecular weight and mass of the components involved in the reaction. The first component, that is carbon dioxide, has a molecular weight of 44 grams per mole and having a mass of 44 grams, as it only needs 1 mole to react. The hydrogen component has a molecular weight of 2 grams per mole, but as having 3 moles to react, it has a mass of 6 grams. Then, both components of methanol and water had only 1 mole produced. Methanol has a molecular weight of 32 grams per mole and a mass of 32 grams, and the water has a molecular weight of 18 grams per mole and a mass of 18 grams.
With the equation of our reaction, we designed the stoichiometric table that let us know the concentration for our reactants and products while time is passing. Therefore, when we have a time 0, we can only observe a concentration for the reactants. But when the time is different from 0, we can observe that the concentration of our reactants will be decreasing according to the process of the reaction. Therefore, also we can see that while this reaction is happening, the concentration of our products will be increasing. Then we use this table in order to determine the amount necessary to feed on the reactor in order to obtain a specific amount of methanol. We established that we had an 80% of conversion. We used this percentage as according to PhD Manuel Soto. This percentage is a good option as a reaction never occurs at 100% of conversion.
Then, for the mass balance, it is suggested to begin with another amount of mass in order to obtain the proportions or concentrations. By adding hydrogen and carbon dioxide, the reactants, we had 50 grams. Then, we made a relation in order to know the molar fraction of both of them. The same we did with the products, having the same amount of 50 grams and doing the same relationship. Assuming a conversion of 80%, we obtain that 10 grams of reactants will not react. In this manner, we obtain how many moles or quantity of products we will be having. It is suggested that the 10 grams that doesn't react will pass through an absorber and then through a desorber in order to separate the methanol from the water and having an efficient process. Assuming that we are required to produce 100 kilograms of methanol for one reaction, we did the relationship in order to know how many grams of each product we will be needed. The sum of it will be 1,562,500 grams of products. Therefore, for reactants, we obtain the moles we need. This represents the 100%. By having 3 moles of H2, there is a stoichiometric proportion of 3 to 1. Therefore, we have a 234,375 grams of hydrogen, this at 80%. If 1,562,500 grams are products, and this is the 80% of the fed, the reactants must represent 1,953,125 grams at the beginning of the reaction. In this manner, we will have that 390,625 grams will be of inert, having 0.9 of H2 and 0.1 of carbon dioxide in molar fraction.
Then we have to calculate the energy balance, and here we have 2 types of energy, the sensible heat and the heat that produces the reaction. First, we have to increase the temperature of the reactants because we have to do the reaction at 250 Celsius, and we calculate with the mass, the Cp of the reactant, and the change in temperature. Then we have to do the energy balance for the reaction, and we have to do with the enthalpies of formation of products and the enthalpies of formation of the reactant. Then we have to sum both of enthalpies, and we have the energy necessary to make this reaction and this process. Well, the economics are simple, We just have to add an heater exchange to up the temperature of the reaction as we mentioned it, and we have to add a separation process. We decide to do an absorption and desorption because they are in gas phase, and it will be more easy to us to obtain this the products of methanol. And we calculate the energy as we see, like if our plant will be in Mexico City and we obtain that price, as you can see in the presentation, that will be the cost of 100 per day approximately, and in 1 year that approximately we work like 254 days in a year. It's like 2 millions and half of pesos of energy of the process.
It's important to discuss some considerations for a safe operation of the PFR. For example, unfortunately, it has some problems for temperature control because some variations as small as 1 degree Celsius may produce an unsatisfactory product. In an exothermic reaction, the temperature will continue to rise as one moves along a plug flow reactor until all of the limiting reactant is exhausted. This means that the temperature will change as the limiting reactant does. It is very important to take in consideration the temperature control because it is something very difficult to control. Because there are some hot spots in the if the reaction is exothermic. Even though it is a very difficult parameter to control, there's a method to achieve this constant coolant flow. Even though this is a very dangerous method because there can be some temperature variation or it can cool down the reactor. It can destabilize the reaction conditions. It's important to know as well that if the reaction mass is cold, reaction rate and heat release will be low, and adding more feed will not raise the temperature. Under these conditions, it is possible to overfeed a reactor, so that when reaction temperature is reached, there will not be enough cooling available to remove the heat released, resulting in a thermal runaway. It's important to mention that the main product is methanol. So, and it is taking place at 250 degrees Celsius, the synthesis. So, taking in account that it is a volatile product, it should be well stored, and the materials for the reactor should be capable to contain any explosion.